Today we're going to be going over some of the ways in which Praat derives all of its acoustic variables. We're going to be going through this mathematically, and we're going to be going through this hopefully at a level everyone can understand, and hopefully it clears some things up about how we're sort of getting all these acoustic variables that we hope to use to build a better way of analyzing people's voice. So let's get right into it. So we have a couple of variables, acoustic variables that we're looking at. F naught, or the fundamental frequency. Fundamental frequency. Excuse my handwriting. That's the first one that we're going to be looking over. Then we're going to have, oh boy, performance. Now look, and these are, I would say, these are the most important. This is the most important variable. Most important. We have jitter and shimmer. And then we have H&R, or harmonic to noise ratio. Again, excuse my handwriting. Okay, so switch colors here. Let's start off with fundamental frequency. So what is fundamental frequency? Well, basically, suppose we have a sound signal, x of t. You know, an x of t can be kind of whatever it wants to be. It can be, you know, say this is time. This is, you know, this is our amplitude. It can be, you know, wee, right? It can be all over the board, right? Whatever the, you know, sound signal is of the kid that is trying to say the word that they're trying to say, in our case. And how fundamental frequency works is all that we're going to do is we're going to do something that looks kind of similar to convolution, but it's a little different in a crucial way that I'll show you in a second. But basically, we're going to be using this dummy variable tau, to, again, this is the part where we're essentially, oh, that's supposed to be an infinity, we're essentially convolving the sound signal, but not quite. And I'll show you as to why in a second. Notice this is t, but basically what we're doing is we are almost convolving, or we're taking the dot product of the function with a time-shifted version of itself. Now, what we're basically going to be doing is, you know, we're going to be, so to speak, plotting r of tau. So for different values of tau in here, this integral right here will have a different value, right? So if this is t, or tau, sorry, tau, this is r of tau. You know, for different values of tau, obviously 0 will always be the highest, but, you know, 0 being the highest because it's the function dotted completely with itself, no time shift involved there, so it'll just essentially square the area. But, you know, it'll be all over the board here, right? But besides 0, besides tau equals 0, there's going to be some other point here that is going to have the tau peak. We'll call it this value here, t peak. And at this value, r of tau, I should say, is going to be like sort of the second highest as compared to 0. So if this diagram here were properly drawn, this should actually be this point here should actually be slightly lower than this point here, but it's beside the point. So basically, we're finding like the second highest value of t, such that we get the highest value we can for r of tau here. Now, all that we're going to do to get the fundamental frequency is we're going to take the reciprocal of this value, and that is it.